Hello, ladies and gentlemen. I'm a freak on the leash, but minus the leash. Today we're going to be talking about partial derivatives and multiple integrations. I'm going to start off by assuming we know at least Calculus 1, and I'm hoping you're more comfortable with integration. Why would we do partial, and why would we do multiple integration? Well, we don't always have single variable functions. Sometimes we're going to have surfaces. Surfaces are okay though. We just have to understand how they behave. I'm going to try to draw this. It's not very beautiful, but it should get the job done. And for reference, this is kind of going to be our y. Here's our x, and hopefully if we get some depth perceived here, we're going to have down on our z and positive on our z, kind of up and down between these two. And so the natural motivation would be kind of think about our gradient vector, which I'm pretty sure I have a video on if that is something we decide to look at. But that's a reasonable place where you would be using partials. That's what they really are, and how you do them is, think about this. We want to figure out how the function changes with respect to a certain variable. It's kind of not clear where we're going to go from the beginning, but what if we let one of our variables be constant and one of them be, well, a variable and vary? What this means ultimately is that we say y is constant. So what we get is, if we have fxy, then we're going to then say, okay, y is a constant. So through what we know in Calculus 1, the derivative of a function with a constant multiple is just going to be the derivative of that function times that constant. So fx here is just going to be the derivative of this function if y is a constant with respect to x. So y. Now this function is not that function, to be very clear. That's just so we can kind of reason it. What this means on the graph is that we take a slice out of it. We take that, and what I kind of wanted this to look like was like that. Call it cubic root, or the or an S-curve, logarithmic curve. That's the intention. And then we say, okay, we get some depth by changing that y. And in this case, the derivative would not look like this. That's just me drawing the curve out and saying that we're taking a slice from it. So that's just the standard rule, is you just treat it like a constant. So if that is all you're trying to learn is how to take a partial, that's that. But I want to do some example work, mainly so I can bring in a gradient and a dot product. Not dot product, but divergence. So we're going to start off with just our gradient of our scalar field f is going to be equal to for every variable that is within the function. So I really should have done f of x in and then for every one, but I think it's pretty trivial to explain. So there we have that, and say we want to find it for function We're going to do that. So to find the gradient of f, we're going to get each of our derivatives. So the derivative with respect to x is going to be equal to e to the x sine zy. Then it'll be fy, which in this case is going to be e to the x, and then we pull out that z. Yep. Cosine zy. Okay. And last one is just going to be fz, which will be identical, except our z and our y are going to be swapped out. And to be very, very specific, you technically get that d variable that you're integrating with respect to, but that's supposed to be 0. So there's the gradient. And because our divergence is so simple, it's just the addition of all of those. You add those together, and you get it. Always a fun idea. Now time for chapter 2, multiple integration. The integral of f with respect to area, dA would be a prime example of it. We're going to assume that we have a nice region. That is the rectangle that we're integrating over is a rectangle, and it's not curvy or wavy. That those two terminology-wise, meaning type 1 and type 2 regions, which aren't bad. I might discuss them in a later video. This is more so trying to get the groundwork where those can then be done, because in those cases, order can matter. So I don't want to make a claim here where it holds for all regions that play nicely with it. I'm sure anyone that's done real analysis or complex analysis can kind of understand that trouble of trying to be careful with what you say with your domain. So yeah, this is going to be the integral, and so this would be x naught, x final. That's not a good f, but I hope it's understood. Y final of f, and then with integration, multiple integration, your order is going to be defined by the insides. So it'd be dy, this is the first one, dx, and then the outer is the last one. You could imagine that by putting brackets on the outside. So in this case, you would go ahead, calculate your antiderivative, plug in your bounds, and you get it. It's not bad. And how you can imagine this as, you can see it as the volume of the shape that is produced by taking that rectangle underneath our surface and bringing it up to the surface, or down, but I don't want to talk about a negative volume. That'd be the absolute value technically. So again, that's me being careful with words. That's that. And when it is this form of a region where both are bounded by not a function of the other variable, but rather by constants. So that'd be a normal rectangle domain, and not something where, in this case, your x is a function of the y, which I believe is a type 2 region in this case. Be careful, don't call it T2. Do not call it T2. That's topological space. I'm being lazy. That's a type 2 though. And then your type 1 is going to be where your y is a function of the x, which is, again, not bad. But not up for discussion. And that's just so I don't give any topologist nightmares. I have the book right there. One of my closest mentors has been a topologist, so I've been taught not to step on those feet. Otherwise, though, I think we're good for today. If anyone has any specific questions, please comment them. If there's any topics that should be reviewed, comment them. I really appreciate all the feedback I can get. I'm going to try to make the audio better. And yeah, that's it. Thanks. Can you stop fighting? Hey, calm down.